This video talks about random variables, and it also discusses a special type of random variables, discrete random variable. So what are random variables? In short, they are functions. So a random variable Rv is a function maps elements in the sample space S to numbers in curved C. For example, we could choose the set curve C as a subset of the real line. So essentially, X maps elements from sample space to numbers. Usually, we consider real valued RVs, real valued random variables. For example, here, X is a real valued random variable. It maps sample space, right, elements from the sample space to numbers from the real line. X is essentially a function, and similarly to manipulating with functions, we can manipulate in the same way with random variables. For example, we could consider the summation of two random variables. We could divide one random variable with another random variable. We could consider the maximum or minimum of multiple random variables. They're gonna generate new random variables. Okay? And there are many functions from the sample space to R. Although not all functions can be regarded as random variables, all random variables are essentially functions. We can also use the notation X in C to denote random events generated by random variables. And this notation here, X in C, denotes the event that containing all the outcomes such that X would map those outcomes to values within this set C. So basically, this is the event. Well, this is a set, also an event containing all the outcomes from the sample space S from the sample space S, such that X would map those outcomes, small s, to values within the set C. Okay, now with this notation, link the random variables with random events, and we know probability functions gonna assign values within 0 to 1 to random events. So this would connect random variables with probability functions. And with the introduction of those additional features, those additional concepts, additional structures, we have a much larger space to explore for our mind adventures. For example, we could extend our definition of conditional probability given events to conditional probability given events generated by random variables. And there are many other random variables with special probability functions. And we could also explore what kind of specific properties they possess. Random variables are functions. There are selected functions with very nice properties. And so are some selected random variables. Here we first get in touch with one type of random variable. So those are the random variables map outcomes to sets of a sequence of numbers A1, A2, A3. I know those are abstract definitions, concepts. So let's visualize those abstractions with a simple example. Consider we throw a coin n times. Let's denote n equals to 10 here. So we throw a coin 10 times. The outcomes can be expressed as strings such as HHTH, THH, THT, well, where we use H to denote head and T to denote bottom, right, tail. So this is one specific outcome such that the first throw is a head, second is a head, third throw gets hit bottom, tail, and then head, then tail. Okay. We could define random events like this, like event hi, if we say I has in total among the 10 throws. And we can also define event tj if we say j tails among those 10 throws. Apparently, we know hi will be equal to Tn minus I, because if we observe I has in total, then the remaining throws would say the tails, right? So if we have I has in total, then the remainings will be all be tails. So this is the equal events, and apparently this is a very cumbersome notations, right? Let's consider a second set of notation. Let x be the number of heads and y be the number of tails. Apparently now we say y equals n minus x, right? Because in total they're gonna be x plus 1, gonna always be n. So n here is equal to 10. And this notation is simpler and cleaner compared with the set notations, and we don't have to work with subscripts anymore. But what are these x and y? Let's take x for example. We know we define x to be the number of heads. Well, we can see that x is essentially a function, that it maps outcome S in the sample space S to a number on the real line. So x is essentially a function from the sample space to the real line. For example, here it shows how the x assign elements from S to elements from the real line. For example, this is the outcome we see. Well, one small s from the sample space S, because it contains 6 heads, x maps this outcome to number 6. Again, this one contains 6 heads in total. X map it to number 6 again. This one has no heads, so all tails. X map this outcome to 0, right? So this is a function indeed. It maps each S within the sample space S to a number within the real line. So it's a real valued random variable. It's a real valued function, actually. And because the outcomes are random, we also call x a random variable. But deep in nature, x is simply a function. We know to define a function, we need to specify the domain, we need to specify the codomain, and the domain of a random variable is always the sample space. So to define a random variable, we need to specify the sample space in most time. And we can define multiple random variables on the same sample space. For example, in this simple example, throw a coin 10 times, right? X could be the number of heads, y could be the number of tails. These are different functions defined on this sample space S. And we could also specify another function, for example, z, which only equals to 1 if the last throw is a head, right? So z would map outcomes such that t to 0 and ht, but the last one is the t, also equal to 0, and outcomes such as t, except the last one, we get a head to 1, right? That only equal to 1 if the last row is a head. So this z is also a function defined on the sample space, maps all the outcomes to values as a 0 and 1 from the real line. So that is also a function defined on the sample space. Is also a random variable, x, y, z. They are all functions. They are all random variables in this simple case. And they all assign number to each outcome from the sample space. Furthermore, take x for example, we could use x to define events, right? Let this notation x in 6 or x equal to 6, this denotes these notations denote exactly the same event. It denotes the event containing all the outcomes from the sample space such that x would map those outcomes S to number 6. So this notation here, these notations, would be the event that we get 6 heads in 10th rows. And we know probability assign values from 0 to 1 to random events to quantify uncertainty. And apparently here, the probability value of this event x equal to 6 will be equal to the probability of this union of events. And each event containing one specific outcome and unique outcome such that it contains 6 heads in total. For each of these outcomes, we know the probability would be, you can pause the video here to think about it. So for each event containing a single outcome, the probability of such would be 1 over 2 to the power 10, right? And how many outcomes here, how many different mutually exclusive events we have here that contains 6 heads in total? We have 10 to 6 outcomes in total. So this is the probability of the event x equal to 6. With the defined events, it's also easy to see that x can only take those values with non-zero probability, 0 till 10, right? It can either be 0 heads, and at most we can see 10 heads in those 10 rows. And this event, the probability of this event, certainly equal to 1 because x can only take those values with non-zero probability. And so together, if we include all those values that x could be equal with non-zero probability, then the total probability will have to be 1, right? And this is a special random variable. Actually, we have a discrete random variable. So what are discrete random variables? A random variable is called discrete if there exists a set such that the probability of x takes values within such set, say, is equal to 1. And this set can contain at most countably many numbers. So you can index all the elements within C with a set of natural numbers. If the random variable can only take values within such set, we call this random variable x a discrete random variable. We could also define the support of the random variable as the set containing all the numbers. Well, this is a set containing all the numbers such that x could take those numbers with non-zero probability. Again, those are abstract concepts. Let's take a look at the simple example we have just seen to concretize those abstractions. So previously, we know x takes one outcome as in the sample space and maps those to a number on the real line, right? So this is one specific example, maps these outcomes to number 6. And x is a real valued random variable because it takes values from the real line. At the same time, it's easy to check that x satisfies the definition of discrete random variable because we can apparently choose this set, say equals x1, x2. Note all the elements in say we are index them. We're gonna index those elements with the natural number, right? So all the elements within C is indexed with the natural number from 1, 2, 3, and keep going, which each number equals to this value. So essentially, we have C equals 0, 1, 2, and keep going. In this simple example where we throw a coin 10 times, and x denotes the number of heads we have, apparently x can only take values from the C, and for sure these events have a probability value equal to 1, right? Because C actually contains all possible values that could be taken by x. So x is a discrete random variable. Of course, the choice of such C is not unique. We can also choose the support of x. And in this special case, in this simple example, we know the support of x is from 0 to 10, right? Because we only have 10 rows. At most, we can see 10 heads. Or if we are not lucky, there's 0 heads. Apparently, x in this support of x, this event also has probability value equal to 1. So this video introduces random variables and a special case of random variables. We also give examples to visualize all those abstract definitions. And thank you for watching this video.